So this is lecture 14 on the gradient vector field, level curves, and contour plots. And basically the gradient vector field is going to give us insight into the geometry of level curves. And the idea of a contour plot is just kind of a natural thing to tack onto this discussion. So we'll see how these things are all related in this talk here. But just to remind you, we talked about partial differentiation last time, and we learned that for a function of two variables, we can define the gradient of f, which we write nabla f, and that's equal to partial f, partial x, comma, partial f, partial y. And so the idea of the gradient vector field is just that we can look at this as a vector, and you can think about attaching this vector at each point in the plane, right? Because the function is a function of two variables, so we can think about attaching this as a vector to each point in the domain and try to understand what it says about the function. That's kind of what we're doing in this talk. So let's get to it. Again, this is page 162 to 169 in the lecture notes for 2020, and my numbering's a little bit off on the things I have printed out here because it's from a couple years ago and I'm too lazy or too cheap to print it again. Anyway, you be the judge. So, gradient vector fields. First of all, here's the definition. If f is differentiable on U, so this is a subset of R2, then gradient f defines the gradient vector field on U. In other words, we assign to each point P in U the vector gradient of f evaluated at P. Now, so it's useful to look at some visualizations of the gradient vector field for some examples, because it's going to give us a lot of insight as to what's going on here. And so here's an example, and I think I can zoom in just a little bit more. I'm going to go ahead and do that. There we go. So this is example. The function that we're looking at here is x squared plus y squared. So calculate the gradient, we get the vector 2x comma 2y. So this is a visualization of that. So the circles in here, we'll talk more about what those mean later. These are actually level curves for x squared plus y squared. I mean, I guess I can just tell you now, a level curve is simply when you take the function and set it equal to a constant. That's the level curve. So like, if I said x squared plus y squared equals to 1, that's a level curve. If I said x squared plus y squared equals to 2, well, that's a level curve. I mean, all we're saying is a level curve has the format f of x comma y equal to some constant. It's the level C curve looks like that, right? And so here's various levels for that curve. And the color coding has additional meaning. Actually, the more blue it is, the smaller the value, and as it gets red, it's getting larger. All right. Anyway, so that's the meaning of the graphic, okay? But these little arrows, they're pointing in the direction of the gradient vector field. So you see what's going on. Like, for example, just to calculate one of them, the gradient vector field at the point, let's say 0, 1, would be equal to, let's see here, we plug in 0, 1 into 2x, 2y, so x equal to 0, so we get 0, and we get 2, because y times 2 times 1 is 1. So that's why we have vectors that are pointing directly up, like along this area here, right? If I plug in different points, I'll get these different vectors by plugging in the numbers. All right. So that's a pretty picture of it. And anyway, that's what the gradient vector field looks like for the function x squared plus y squared. Another example. Here's the gradient vector field for x squared minus y squared. So x squared minus y squared, if you set that equal to a constant, that gives you hyperbolas, right? So if c is positive or negative, we either get hyperbolas which open up or down or left or right, depending on the value of c. I'll let you figure out which one's which. Oh, fine, I'll figure it out. let's see here, x squared minus y squared equals to 1. Is that open up or down or left or right? Well, if you think about it, if x equals to 0, we get minus y squared equal to 1, which has no solution, right? So this has x is not equal to 0 for this curve, right? X is not equal to 0 for this curve. And if x is not equal to 0 for this curve, that means that it doesn't cross the y-axis. So x squared minus y squared equal to 1 is a hyperbola, which opens sideways, all right? So these guys are level curves with positive c, and these guys are the level curves with negative c. And if you look at it, think about it, the larger c gets, the further out you go here, right? And the more negative c gets, the further out you go. The more negative and large gets, you go out there, right? So if you start looking at it, you'll start realizing that these arrows are pointing in the direction in which the level for the curve is increasing. It was easier to see up here, right? Because when we think about x squared plus y squared, oops, sorry to scan down here. When we think about x squared plus y squared equal to a constant for the previous example, you know, that's a circle, right? So as the radius gets bigger, the circle, where get to further circles out, and as you look at it, the gradient vector field's always pointing in the direction of circles of larger radius, which is to say that the gradient vector field points in the direction you should go to level up. So if you want to go to the next level up, you should follow the direction of the gradient. If you want to increase the value of the function, go in the direction of the gradient, right? So there's that one, right? It can be more boring. Here's a nice boring one. If we look at the gradient vector field of the function f of xy equal to x, you calculate the gradient, you straight up get x hat. So here is a picture of x hat using this visualization. We've got arrows which are pointing to the right, and the level curves of x are just vertical lines, right? X equal to 1, x equal to 2, x equal to 3, x equal to minus 1, minus 2, minus 3, and so forth. There it is. All right. Let's see here. What else can we understand about this gradient? Of course, obligatory. If I can do x, I can do y. And if we look at the gradient vector field to y, the function y, we just get y hat. It looks like that, right? And so actually, this is kind of neat because maybe we just found a way of characterizing the unit vectors in terms of coordinate functions, right? And in fact, that is true. We now have stumbled into a way to use calculus to derive the unit vectors, right? If you have a non-Cartesian coordinate system with, say, y1 and y2 are coordinates, then you can write y1 as some function of the Cartesian coordinates and y2 as some function of the Cartesian coordinates which define it. And then you can calculate unit vectors by calculating the gradient of f1 and the gradient of f2 and then normalizing it. So this gives us a method actually to calculate the unit vectors of non-Cartesian coordinates using calculus. And here I'll actually go through it for the polar coordinates. I think I'll do that here. Let's see here. So polar coordinates, we define those by r is equal to square root of x squared plus y squared, and theta equals inverse tangent of y over x for x positive. I'll focus my calculation there. If we calculate the gradient of r, we have partial x of the root of x squared plus y squared, and likewise for y. And when we differentiate, we get 1 over twice the square root times 2x. The 2's cancel, leaves you this. And likewise, 1 over 2 times the root times 2y upstairs, but then the 2 from the differentiation of the root and the 2 from the derivative of the inside function cancel again, leaves us that. And but that's nothing more than x over r and y over r. But you might remember x equals to r cosine theta, y equals to r sine theta, so we can realize that that's nothing more than cosine theta sine theta, which is exactly what we defined r hat to be before. Of course, there's no normalization in this case. It just so happens that when we calculate the gradient of the r function, we get a unit vector field. So that's kind of cool. In contrast, the gradient of the standard angle function, well, that one's a little more interesting because that one, we end up differentiating this inverse tangent function, And that, of course, gives you 1 over 1 plus the thing squared times the derivative of the inside function, which by the chain rule picks up a minus. So I've skipped a little calculation right here. It would be healthy for you to show that this derivative, I would encourage you to work this out. Convince yourself that that partial derivative is equal to this, and this partial derivative is equal to that. It's not immediately obvious, but it's a calculation everybody should do. The reason that this is that and that is this, it's not quite the same reason. It's a little bit different because here the variable is in the denominator, here the variable is in the numerator. So the calculus is a little bit different. But anyway, that's why you have a minus for the one and not for the other. And anyway, you get that. But when we calculate the length of the gradient of the standard angle function, we actually end up with 1 over r for that length, because notice that minus sine theta cosine theta is a unit vector. So the length of gradient theta is 1 over r. And so to find theta hat, we divide by 1 over r, and we're just left again with theta hat equals to minus sine theta cosine theta. Now again, I do think you can derive these geometrically fairly easily, but the cool thing is that this idea will also work just as well for functions of 3 variables. Here's a picture of the gradient vector field for the radial vector radius, a radial function, and here's a picture for the gradient vector field for the standard angle function. As you can see, the computer algebra system I used to plot this, it has trouble at x equals to 0, right? And so that's not a real feature. Like, that's an artifact of the fact that computers have a hard time figuring out how to do standard angle all the way around, you know. But anyway, there it is, theta hat, it's minus sine theta over cosine theta. And the larger point from all this I'd like for you to see from these things we've looked at is that if we think about the level curve as f of x y equal to k for some value k, and if we consider some point x naught, y naught on the level curve, then the gradient at that point, what that's going to do is it's going to be perpendicular to the tangent line of the level curve, right? So like, if this is the level curve, and this is the point, x naught, y naught, you know? And then like over here, there's a higher level. So maybe this is c, maybe this is c prime, and suppose c prime is greater than c. So the function's like leveling up in that direction. Then the tangent vector to that curve, right? This tangent vector to that curve is going to be perpendicular to the gradient vector. The gradient vector is going to point out like that. All right, that's going to be where nabla f of x naught, y naught. Sorry, I'm writing out of frame there. Let me fix that. There we go. So again, you have a level curve, another level curve with a larger constant. So there's a tangent to the curve at the point x naught, y naught, and that gradient vector field is going to be pointing away from the curve in the direction to level up. That means also it's going to be perpendicular to the tangent line to the curve. If we wanted to stay constant, we could follow the tangent line. The tangent line is going to be in the direction in which the angle between the gradient and that direction vector for the green line is 90 degrees. And remember our previous talk, that would mean that the directional derivative of the function in the green directions is 0, which is to say the function is going to stay constant along those green directions, which of course makes sense because a level curve is exactly the set of points along which the function stays constant. So let's see here. The gradient vector field nabla f is perpendicular to the level curve, is the thing that we should take away from the examples. Now, if you don't believe it, well, good for you. Don't believe it. We will prove it with calculus in a soon coming lecture. So don't worry. That's in a future section though, because I need the chain rule to do that argument justice. All right. So stay tuned. We'll get back to it. Next example is a physical example. Suppose you're looking at the voltage function. All right. I'll get it in frame here eventually. Sorry, folks. Suppose you have the voltage function v of xy is 1 over the square root of x squared plus y squared. That represents the voltage due to a point charge at the origin. And the electrostatics, the theory of electrostatics states that the electric field is minus the gradient of the voltage function. So geometrically that has a simple meaning. It means that the electric field points in the normal direction to the level curves of the voltage functions. And because of the minus, it means that the voltage is, it means that the electric field points in the directions in which the voltage lowers. So the electric field will point in the direction in which we go to lower voltage. That means it pushes positive charge to regions of lower voltage. If you've had a course in physics, these statements I'm making should be familiar to you. Of course, the level curves of the voltage are commonly called equipotential lines in physics, and those equipotential line is just a line in which the voltage has a constant value. And so for this one, if you set v equal to a constant, you got nothing more than a circle. And so let's see here. So the gradient, you notice that the gradient of the voltage function ends up being partial derivative of 1 over r, partial derivative of 1 over r, and by the chain rule that's minus 1 over r squared times partial x of r, and minus 1 over r squared, partial y of r. But you can, well, we calculated this just a second ago in the previous example, and we found that that was r hat, so I'm just using that result again. Alright, so the equipotential is 1 over r, simply circles, and the electric field is a purely radial vector field. It just points out in the unit radial direction, and it drops off as the reciprocal, the square of the distance from the origin. Let's see here. Next example. Let's say consider the ellipse x squared over a squared plus y squared over b squared equals to a constant k. Sorry, I'm out of frame. Fix it. So there the gradient vector field is 2x over a squared x hat, 2y over b squared y hat. That is going to point in the normal direction to the ellipse. So that's pretty neat. I wonder if I have a picture of it. If I don't, my apologies. Oh, I don't. So lazy. If you consider the hyperbolas, I don't know if these are actually hyperbolas. They're kind of like hyperbolas. See, I don't remember the technical definition of a hyperbola. This might not technically be a hyperbola. It kind of sort of looks like a hyperbola, but it might not technically be a hyperbola. Definitely if it was xy equals to a k, it would be a hyperbola, but I question the use of this word here. So I'll have to go talk to the editor of my notes. Anyway, whatever the name of these curves are, the gradient to g is 2x y squared x hat and 2x squared y hat. That will point in the normal direction to this curve. So when k is positive, we have y squared equals k over x squared. So y is plus or minus root k over x. And when k equals to 0, we get k equals to 0, we get the coordinate axes, right? And oh, so the next one, the next example, I actually have the let me try to see if I can get them both in the thing so you can see the difference. There we go. So example 40, well, this example I've got x squared y squared. The next one I've got xy equals to k. I think this is the genuine, the real McCoy here, so to speak. It's this guy, the level curves are actually hyperbolas. And the gradient vector field is, a little bit simpler. It's nabla f is yx hat plus xy hat. If this notation is confusing you, remember that that's just like another way of writing y comma x, right? And this is just another way of writing 2x y squared comma 2x squared y. All right. And I do have a picture of these guys down here. And so I say nabla f, which is the hyperbolas, is on the left. And nabla g, which is the, whatever you want to call those things, I don't have a name for them. Squared hyperbolas. I'm not sure what these things are called actually. But the curves of the form constant equals to x squared y squared, those over here, and as you can see, they are different different level curves, right? Here I'm actually plotting z equals to x squared y squared in red, and z equals to xy in blue. Of course, z equals to xy is much lower, right? And z equals x squared y squared is much steeper, and also it's always positive, right? xy, in contrast, dips down below the xy plane when you're in quadrants, when if just one of the coordinates is negative, then z is going to be negative, whereas z x squared plus y squared is always positive, so it kind of looks like that. So here I'm looking at z equals to the level function. Okay. Notice that the whole discussion of level curves is happening in the plane, right? So, and so I'm sort of transitioning here a bit. That brings us to the topic of contour plots. Maybe you've studied what's called a topographical map before, right? A topographical map uses two-dimensional chart to plot a three-dimensional landscape, right? And so the idea of a contour map is to make similar graphs for graphs of the form z equals f of xy. I say to form such a plot, we simply imagine projecting the graph into a few representative z values, either down or up to the xy plane. This is like really useful because, of course, we can look at two-dimensional plots, but it's hard to do 3 dimensions justice. And so I illustrate that here. So what we're looking at now is some actual contour plots with the corresponding graph. So, all right, let's see here. Get it so we can see the start of this guy. So what you're looking at now is so we're looking at the function 2x plus 3y, all right? So if you set that equal to a constant, you get lines of slope, slope minus 3/2, I think. These all have slope minus 3/2, okay? Is that right? If I solve that for y, I get k minus 2x, I divide by 3, I get, oh yeah, minus 2/3 there. Is that better? 3/2, listen to me. So if you solve for y, you can see that the slope of every one of these is minus 2/3. So they all have the same slope, they're parallel lines, right? And those are the contours. And so this is the picture of z equals f of xy. All right, so you could look at this or you could look at that. This also gives a description of the so-called contour plot of that plane. Now, to make this better, we should actually add numbers numbers to tell you which level these are. And unfortunately, I don't have those on there, but to make a more detailed, a more helpful contour plot, you would add numbers to add the contours. Just like if you're looking at a topographical map, the really good ones, if you look on there, you'll be able to see the altitude for particular level curves, let's say. So here's another one, x squared plus y squared. So z equals to x squared plus y squared is a quadratic surface known as a paraboloid. And the level curves here are just circles. And so here's the contour plot. Down here, just circles. And the color coding matches up here, by the way. That's part of the reason I don't have numbers, and it's okay. The software I used, which I think was Maple, a few versions ago, but the colors match. So like the red part corresponds to the red part, and these blue corresponds to the blue, and it's just looking at a square window of the domain. Of course, this thing goes on and on. This is just looking at a piece of it, right? Another example is the x squared minus y squared function, and this time the graph is what's called a hyperboloid. Here's a picture of it down here. If I can get that in the picture. Let me do a little old school editing. There we go. So Alright, yep. So here we have, again, the level curves are hyperbolas that open up or down or left or right, for depending on whether we're positive or negative. Apparently the positive ones are opening left and right, and the negative ones are opening up and down, because that's the part of the graph which is lower versus the part of the graph which is higher. And so there you go. And then the origin is what's called a saddle point, because in that origin place, you see you can go up if you go that way, right? But then you can go down if you go the other way. It's hard to see things in a printout of a 3D graph. But over here, so these level curves are smaller, these level curves are larger, so if you go that way, you're going up. In other words, if we go horizontally, like away from the origin, we're going up and up, up and up. If we go up, we're going down. So if we go up the positive y-axis, we're lowering our levels. If you go that way, we're lowering the levels. So that's why it's a saddle point, because in one direction, you increase the values for the function, but in another direction, you decrease the values of the function. And at that middle point, 0, 0, the gradient is 0, right? Because remember, the gradient here is 2x minus 2y, so when x and y are both 0, then we have 0, 0. 0, 0, the origin, is a critical point. Another example, let's see here, let me undo my editing. There we go. Another example is just, kind of interesting. Sorry, I'll get it in frame here eventually. Cosine x. If we just look at f of xy equal cosine x, then that makes z equals f of xy kind of a wavy plane. And so what I'm describing here are what the level curves look like. Level curves are vertical lines, and you get, what else am I doing here? So I figured out where k equals to 0 goes. K equals 1/2 looks like this. K equals 1 looks like that. K equals minus 1 looks like that. I figured out that the gradient of f is 0 along the plus or minus 1 contours. So like the plus or minus 1, sorry, I'm out of frame. The plus or minus 1 level curves are actually where you have actually maximums or minimums, as it happens. Those are places where the gradient is 0. So spoiler alert, if we want to find where the function's maximized, or minimized, we look for places where the gradient is 0. And so we'll be talking about that in more detail in a future lecture, right? But really, it's all here. It's all here. Once you understand the geometry of the gradient, you can maximize functions of 2 variables. And functions of more variables, it's kind of the same story, but we can't visualize it the same way. Anyway, here's the level curves for the cosine x. Of course, it's got it repeats itself, right? Because that cosine 2x has that 2 pi periodicity. And here's the graph, and you can see the relation between the level curves and the graph. Level curves, easy to plot. Graph, I don't know many people who can freehand 3-dimensional graphs like decently. Maybe art majors, right? Okay, so I think we may be having some numerical artifacts here, right? Like the rendering of the level curves here is not quite right, right? Look at that. That's numerical garbage right there. You got to know what you see. You know when you see it. It's not that the function's actually wiggly like this. It's that we're beyond the resolution that the computer algebra system can do decently. And so the curve we're looking at here is cosine xy. And so there's your gradient minus y sine xy minus x sine xy. And so critical points are going to be where basically x times y is n pi. That makes both of the signs 0, right? Remember, if we plug in n times pi, an integer multiple of pi, that makes sine 0. So we got tons and tons of critical points. Like the critical points are there's whole hyperbolas, right, along which the gradient is 0. And so like, anyway, and you can kind of, well, I don't know if you can see it or not, but if you look at it, it's got lots and lots of hills and valleys because, well, cosine of xy, z equals cosine of xy is a rather interesting graph, right? It's at most 1. It's between plus or minus 1 because it's, after all, cosine. But it does a lot of funny stuff there, right? Anyway, and then finally, okay, so imagine yourself without a computer. Perhaps the robots have taken over. We're in the robot holocaust. So what else can we do? We can draw contour maps by hand. I do it all the time, actually, in class. It's not a big deal. You can draw some contour maps by hand, and you can get a lot of information pretty fast by doing this. What I can't do by hand decently is here's what I don't try to do by hand, or at least I try very hard to avoid it. These kind of plots, like plotting the vector fields, this is not something you want to do without technology. Level curves, that I can do. Gradient vector fields, it's not a good use of time. But anyway, here's the, if I look at the function square root of 1 minus x squared minus y squared, that's my f of xy, then if you set that equal to a constant, you get circles. And if you look at the graph, it would look like this. But you can see, so this is, getting back to my original comment, you can construct the contour map by taking the graph of the function and putting some like traces on it, some curves of intersection at particular horizontal values, and then you just imagine kind of pancaking them down into the plane, and that gives you the contour map. That's the relation. Or you could think about these as kind of like rings of an onion or something that you could imagine just kind of like popping up out of the page to build the graph again. So anyway, there you go. Level curves and contour plots. That's what they are. And we'll talk more about their calculus in the upcoming lecture, I think. Or let's see, what's our next lecture? Well, 15, right? So actually, we're doing partial differentiation of 3 variables next, and I think actually lecture 17 will return, and it's either lecture 17 or 18 will actually prove some of the claims I made just on the basis of looking at examples today, which of course is not a proof, it's just, all we can do at the moment. So, thanks.